Like everyone else, we were funded by the federal government, but also Dairy Australia, and we had a partnership with the Tasmanian Institute of Agriculture in our work. The team, a fair few of us from the University of Melbourne, probably worth mentioning Andrew Smith, who's moved on from the university, Rochelle Meyer, Karina Marsden joined us from Bangor University as a Marie Curie Fellow. She's gone back to the UK. She was in isolation in Melbourne for a year, and then we sent her back to isolation in the UK for a year. And then Esme Duluth joined us from Wageningen University as a master's student, so I'll cover a little bit of what Esme is doing. And then the Tasmanian Institute, Richard Rawnsley, Karen Christie and Matt Harrison worked on the project as well. So our objective was to basically take the best management practices for dairy and kind of challenge them. We were involved in developing these best practices for dairy probably over 25 years ago and wrote the sort of first best practice guide for dairy. But they hadn't really been sort of rigorously evaluated. And so part of this study was taking the modelling tools we had and just challenging, do those best practices stack up in the subtropics versus the temperates, irrigated versus dry land, rate, source, timing, placement of nitrogen fertiliser. Then obviously to use that to say, well, are our models adequate? And continue to develop modelling capability. So we took each one of those best practices and looked at them in terms of soil types, climate, seasons, years, using the model called DairyMod. So DairyMod is a whole farm systems grazing model, has about 10,000 lines of code in it, so it's quite mechanistic in the way it works. And we took sites from the subtropics through to cool temperate winter rainfall as well. Now, the first thing that was interesting was looking at this cutting versus grazing relationship, because a lot of the early experiments in nitrogen response were done under cutting, and it ignores the massive amount of nitrogen cycling through the animal, which can be 200 kilograms of nitrogen per hectare per year. And so we were facing some of the seed companies saying, well, our new variety grows to a higher, and you need more nitrogen on our new variety. And actually they didn't when we overlaid their response curve with our response curve under grazing. It was just the accounting for the mineralized the cycling of nitrogen. So you can see there what we've circled is the 90% of maximum observed yield in both cases. And you can see basically if you expand that out to a 12-month period, you get about 200 kilograms of nitrogen per hectare per year difference between the two response curves. So what did we work on the theory of nitrogen fertilizer? So most nitrogen fertilizer dry matter yield responses work on this diminishing returns principle, where you get to this point where you've met the soil plant system's capacity for nitrogen in any one grazing rotation. What we decided to work on was the 90% of maximum observed yield in each case. So that's what Y90 is. And then you drop it down to say, well, maximum yield at this Elliott Research Station case was 143 kilos in that spring grazing rotation. Yes, it was a fairly ideal growing conditions for ryegrass. But if we wanted to be efficient, 50% of the nitrogen was being applied above the 90% point. So if you brought it back to 90% of maximum, you're only applying 60 kilos of nitrogen to get the majority of that response. So do you want to spend that second 60 kilos of nitrogen to get another margin on that? Because this is what happens to the loss response. So the end losses are exactly the reverse of that, because you have exceeded the soil plant system's capacity. So this is what we found at a number of the sites we were looking at, was the percent reduction from that Y max coming to the 90% of maximum. We saved about 50% of the nitrogen, probably more in most cases. But look what happened to the reduction in nitrogen loss. So definitely in terms of best practice, sticking with that 90% at the sort of top part of the diminishing returns curve is where we should be recommending. But the problem is it doesn't stay at a constant rate at all sites all the way through the year, and that's where we went next. So you look at the annual production responses from the model, and you can see the different sites have different shapes of that response curve. Some sites are responding to a higher rate of nitrogen, some are responding to a lower rate of nitrogen, some are not responding as much in dry matter yield response because they have other limitations. You know, you can pour a whole lot of nitrogen on. So before you get too concerned about those big numbers on the y-axis, we've done experiments putting on over 1,000 kilos of nitrogen and seen a response close to that. But you've got to account for a lot of other things in those experiments, like they might have been done under cutting, like this was done under cutting. So you've got to take 200 off that x-axis straight away to get something that's that would be under grazing. So when you break it down to the seasonal response curves, we ran the model for 20 years at each location, and that's what you've got in those box plots there, where you've got 20 runs of the model in different seasons and different times of the year, and the variance you get in those. So where you get a tight variance, obviously it's a fairly predictable response to nitrogen. So you could see annual ryegrass at Taree, for example, in winter, which is the top row, winter's the top row, a fairly predictable response. But straight away, if you come across to Mount Gambier in winter, you can see the response isn't quite as good as annual ryegrass at Taree. That's pretty obvious. You're growing annual rye in the subtropics as opposed to perennial rye in a cooler climate. So first of all, the rate doesn't stay at the same point. Go down to spring response at Mount Gambier, far better, but responding to a higher rate of nitrogen. But if you go to Terang in spring, you've got a high variance there. You've got some years where the end response is pretty much flat. And so you can see as you go down through this whole mix that the nitrogen response varies by season, by site, by system, irrigated, dry land, and depending on the species you're applying it to. That Kikuyu one there, massive variance because it's in a highly variable rainfall. It's not irrigated Kikuyu. Some years you get great rain and you get great response to nitrogen, other years not at all. So I guess there's a point there. And this just takes that and shows you the Y90. So what is the optimum rate that the model said you should apply to get 90% of maximum yield with the standard deviation at each of those sites in each season? And just generally looking, the Y90 differs depending on the site and the season. So how do we recommend on that? Then the other study we looked at was what Helen was talking about, the autumn response to nitrogen. This is something that's worried us for a while in Victoria, where the old best practices used to say, the moment the autumn break rains start in Victoria, put on your first dose of nitrogen because you'll get a response to it. And this suggested that at least at Ellenbank and Terang, 22% and 50% of the years you got a zero response to nitrogen in the autumn break. Simply, there was just not enough soil moisture. The first rain that you get, the first 25 mils, hasn't actually even wet the surface. The subsoil moisture is completely missing still. Then it also depends on what kind of summer you had. If you had a wet summer with rainfall all the way through, then the residual nitrogen has been extracted by the pasture growth, so the soil is quite deficient in nitrogen. If you've had a very dry summer, you've got a lot of mineralization that's happened, and a lot of nitrogen sitting in the soil. There can be 50 kilos of nitrogen sitting in the soil, so don't expect to get a good response to nitrogen if there's already a lot of mineralized, unused nitrogen sitting there. So that changed our recommendations to basically say you've got to wait until you actually get the soil moisture adequate and plant growth starts before you put on nitrogen in autumn. And that's where the mineralization calculator becomes quite important as well. We also looked at, and it probably shouldn't surprise you, under irrigation. If your irrigation is dodgy, well, your nitrogen response is going to be dodgy. It's a very technical term, that, dodgy, but it works. So the rules we set in the model at the Elliott Research Station were quite tight, and they were very responsive to the conditions of the Krasnozem soil, so it was a very responsive system. At Mount Gambier, we had a big debate about this, but we decided to set it on the rules that the centre pivot was operating on, which turned out to be suboptimal. In good rainfall years, it was adequate. In poor rainfall years, it was inadequate. And so what you see there is how even under irrigation, you can get variable responses to nitrogen if you don't get the irrigation right, because some years it was suboptimal water. The other one is why do we stick with this Y90, X90 approach, and that is the N losses versus N rate. You saw a previous version of that, but here's where we've converted the environmental loss against the relative yield, so the proportion of maximum yield that we could achieve on the y-axis, to show you that in all cases, at about 50 to 60 kilos of N per hectare per year in an application, you start getting to that point where the N losses start becoming exponential because you have exceeded the soil plant system's capacity to utilize that nitrogen. So that's why the best practices would cut off the nitrogen somewhere between 50 and 60 units of nitrogen per application. We also looked at the concept of, well, when we first came out with these best practices, we were saying apply nitrogen strategically as and when the plant needs the additional dry matter. And very quickly the whole industry moved to a fixed recipe of putting the same amount on after every grazing. And so we compared that and said, well, what if we did at this particular site? Our model said for winter and spring, the flat rate would be about 23 kilos of N per hectare per year. The model suggested in these particular seasons 19 and 40. So this is quite different. Well, the 19 is not that different, but the response we got to the flat rate, 1.2 or 1.7, the adjusted rate, okay, we dropped the nitrogen rate in the case of winter. We were able to put on less nitrogen, get the same dry matter yield, and obviously making more money out of it. In spring, we were able to dramatically increase the nitrogen rate and get a response to that of an extra 2.1 tons of extra dry matter as a result. So that really emphasizes that you shouldn't be applying a flat rate of nitrogen. Sometimes it is inefficient. Other times you're undercooking your pasture growth that you could get. This was an interesting study that Andrew Smith did, where we looked at what if we had increasing levels of precision knowledge about the system? How much would that improve our ability to time nitrogen? And so the codes here are, the ZR is 0, so that's no nitrogen, a control treatment. FR, flat rate, so that's a monthly flat rate of nitrogen all the way through the year. And then the rest of them are increasing levels of knowledge about the system. So strategic is where the model told us we needed to come in to apply nitrogen and to keep the Y90 going. Then the P's versus the D's, the precision soil, precision plant, we got the model to tell us when the plant was 10% deficient in growth rate because of nitrogen, or the soil was deficient in growth rate by 10%, and then it would apply nitrogen either monthly or daily. So the last two are daily applications of nitrogen. So you can see increasing levels of precision knowledge. So first of all, in terms of fertilizer, you can see definitely moving from a flat rate of nitrogen, a constant recipe, to more strategic approaches to nitrogen saves you on nitrogen fertilizer. That's a no-brainer, really. What was quite significant, okay, obviously you get an increase from a control treatment up to some form of nitrogen fertilizer being added, and that's what you see there. But what was notable was that increasing levels of precision were not giving us more production. So moving just from a flat rate of nitrogen to strategic didn't change the outcome. But in terms of end losses, it made quite a big difference. So from the control to putting on a flat rate, you lost a fair bit of nitrogen. Then as you went to this, what we recommend is strategic, well, we dropped the nitrogen losses by being more strategic in the nitrogen we applied. But then as we applied increasing levels of knowledge and sophistication, we weren't actually getting better at the nitrogen use efficiency. So I guess the message out of this is just moving from a flat rate of nitrogen to more strategic consideration of the soil plant potential and applying the right rate for the right conditions is where you get the majority of your benefit in terms of best practice. Moving to increasing levels of precision beyond that might be a good idea, but actually, instead of nitrate sensors in the soil, actually a soil moisture sensor was far more useful in this case to tell us what response we're likely to get. So if you want to go for precision, don't go for nitrate sensors, go for soil moisture sensors. To the question that was raised earlier about, I think Deli, you raised this, about putting money in the bank. We've had this question for quite a while about what would be the fate of nitrogen applied in the late drying period, say in November or December? Are we investing it in the mineralization, in the soil mineral nitrogen pool? And so we ran a study here just looking at two different soil types, either putting on the nitrogen in spring, when we expect that 100 kilos to be quite efficiently utilized. And so the plant's going to take some of that up and not invest a lot of it in immobilization. But if we put it on in December, when soil moisture is very, very deficient at that time of the year, there's not a lot of plant growth, but would it get immobilized into the organic matter and benefit the system later? There's also the issue of hedging your bets, because a lot of farmers in November, December in Victoria would say, well, do we or don't we put on that nitrogen? Because if we get a good response to that nitrogen, it's actually worth a huge amount back to the farm. But if we miss it, if we don't get a growth response, have we lost that nitrogen? And the model is suggesting we didn't. So what it really showed was where you've put the nitrogen on, so if you compare the top two lines, which is the same soil type either with the nitrogen on in spring or that nitrogen on in the dry summer period, it clearly says that we've invested that into the mineralization pool and it's coming out constantly, elevating the potential response to that nitrogen all the way through the year. And that happened on both soil types. When you look at that on a seasonal basis, sorry, it's a bit difficult here, but if you're comparing the first two bars, the second two bars, as a soil type within their own right, you can see that for at least 6 to 9 of those months, if you look at the little stars, at least 6 to 9 of those months in each year, we were getting a benefit, a consistent benefit in 6 to 9 months for having put on the December nitrogen. We were only getting a benefit to the spring nitrogen in 2 of those months. So that's fairly obvious, because you put that nitrogen on in the peak of the spring growth period, the 100 kilos went on, the plant used it, and it produced growth. But the putting it on in a dry system where the immediate demand of the plant wasn't there, it seems that the model was suggesting it was investing it in the organic matter, immobilizing it, and then it was coming out consistently later. So, Delhi, there's your next research proposal, so you can actually prove that to us. The model says, but is it true? We'll have to put it to the test. The Esme Deleuve's study was looking at an age-old question we've had of, are we putting on too much nitrogen for animal health? Feeding a dairy cow on more than about 18%, 20% crude protein, the animal starts spending of its valuable energy to metabolize the surplus nitrogen in its blood and excrete it in the urine. And so not only do we lose energy in the animal, but we actually create a higher nitrogen loading in the urine as a result of too much nitrogen. So what Esme did in this study is created a spreadsheet model where we had a whole cow energy balance model in one page, a whole cow nitrogen model, and then we tied the two together and put 4 farm case studies through that. What it suggested is the New Zealand industry's got a problem, but we don't really in Victoria. The reason being is they don't supplement with energy, they don't supplement with grain. So their cows in New Zealand are getting a large amount of nitrogen with not the energy to metabolize that surplus nitrogen, and so they're loading their cows with an energy deficit at times of the year. What we showed when we put through those 3 scenarios you can see there is the better scenarios, the scenarios with less milk loss, was where we were supplementing with grain. The scenarios like the blue scenario was a high nitrogen fertilizer pasture with no grain supplementation, and we were losing milk at different times of the year relative to what we could have. So very clearly, if you are feeding cows on a pasture that has high crude protein, they will lose energy, they will lose milk production to metabolize the surplus nitrogen in their system. But if you supplement it with grain strategically, you've addressed that energy imbalance. So the outcomes for the industry, we confirmed the 4 R's, the rate, source, timing, placement of nitrogen. They are effective, but we can improve on them rather than apply a flat rate. We can be more nuanced in the strategic rate. Rates of 20 to 50 kilos will ensure adequate nitrogen, but it's more efficient to adjust those strategically depending on the situation. There were some cases like Elliott Research Station in the middle of spring where it's almost utopia for growing ryegrass. It's that 16 degrees, it's no moisture limitation. We could get a response well above 60 kilos of N, and I think that's real. Y90 definitely reduced the amount of nitrogen fertilizer required by going to 90% of maximum, and it reduced N loss by somewhere between 37 and 74% relative to putting on more nitrogen. We identified the same as Helen did, the autumn nitrogen response, particularly following a dry summer, a poor response. And the Kikuyu annual ryegrass study we did, Dave, sorry, I didn't actually include the graph in here, I don't think. We found that applying nitrogen to the annual ryegrass period of the year was definitely cost effective because it gave you a return on investment. You've put money into putting that oversowing in. You need to get your 6 to 8 grazings out of it to get a return on investment, and you wouldn't get that return if you didn't put nitrogen fertilizer on it. We did find that it was pretty marginal value to put nitrogen on the Kikuyu phase. And the whole story about a deficit of nitrogen coming out of the Kikuyu phase into the autumn break really didn't show up in the model, saying that if you didn't fertilize the Kikuyu, you would have a nitrogen deficit. We didn't find that significant in the model. I think a few speakers have mentioned the brochures. So the dairy team, we worked together, Dave, Helen, myself, the team came together and looked at the best practices and how our work would need to update what was written in those best practices. And so Graham Ward in particular helped us pull this together. And then we had a number of publications, I think conference papers, a master's thesis, and YouTube videos like everyone else. That's it. Thank you.